Hello Year 13. I'm using this video today to describe to you how to use the Trapezium Rule, which is something that you might be familiar with, but it's something we're going to do in more detail today. So what it does is, as you can probably see from the picture, we are attempting to find a definite integral, that is an area underneath a curve, but we're only doing it approximately. Okay, we're using nice shapes that we can calculate easily in order to approximate the area, and of course we're using trapezia to do it. So the idea behind this is that not all functions can be easily integrated. There are lots of functions that you could probably think of that don't have very nice antiderivatives that we can calculate easily and get exact values for our area. X squared is not an example of that, but it's a nice one that we can use to demonstrate with an example. So I want to approximate the area underneath this curve of x squared between 0 and 3. That's my lower and upper limits. And I'm using 3 equally spaced trapezia in order to do that. So my trapezia goes 0, 1, 2, 3. That's going to give me 4 points, bear in mind. And if I know how to find the area of a trapezium, I can find these areas and add them together. And clearly, if I were to increase the number of trapezia, my current overestimate, because of these gaps at the top above the curve, is going to shrink and it's going to converge to the actual integral, which is going to be something like 9, which is given by the sum over there. Okay, let's go back to 3 then. So we're not doing it as thinly as this. We're going to go back to something more manageable. So 3 trapezia is nice because it fits nicely on my unit intervals. So to start with then, let's remind ourselves of what the area of a trapezium is. And I'm going to draw them upright as they're normally going to look in this picture. So I've got parallel side, and then base, or if you'd rather height, and then this bit. Let's call this H, let's call this A and B. So recall the area is going to be a half times the sum of the parallel sides, which is A and B. These are always going to be vertical in our diagram. And then multiplied by the distance in between, which is H. Okay, that's going to be important in figuring out, firstly, how to do this first example, and then how to get a formula for how to do this in general. So let's label up our 3 trapezia. Even though this first one is actually a triangle, we can still consider it to be a trapezia if we think about A being 0. So A, B, C. And then separately, let's do these areas. So area A is going to be half. And then the parallel side, you'll notice, is 0 and 1. But these are y values. These are what you get when you plug these values into the function. So I've got, I'm going to write it firstly as f of 0 plus f of 1. Okay, I know that that's going to be 0 and 1, but it's helpful to notice that down. That's going to be a half. Oh, I've forgotten the distance in between. That's going to be 1 because that's how far these are apart. Then I'm going to fill in the values. So this is a half, 0 plus 1 times 1. Great. Okay, what's that? That's going to be a half times 1 times 1. That's going to be a half. Okay, let's do B next. So B is definitely a trapezium this time. It's a half, but this time it's f of 1 for this height and f of 2 for this height, 2 and 4. F of 1 plus f of 2. Again, times 1 in between. That's a half times f of 1 is 1, f of 2 is 4. And then times 1, that's a half of 5, that's 5 over 2. And then finally C is going to be a half at the front, and then f of 2 for the first height, and then f of 3 for the second bit. And then again, times 1. Okay, a half, f of 2 is 4, f of 3 is 9, and then times 1, which gives us a half of 13. Okay, summing these up should give us 9.5. Let's double check that. Equals 1 plus 5 plus 13 over 2. That's indeed, what's that? That's going to be 19 over 2. Yes, that's 9.5. Okay, great. Right, so hopefully you can see some kind of nice patterns in our initial example here. All of these values in the brackets are values of y, which is what you get by plugging in the values of x. And also we get some nice overlaps. Because of how this is moving between the overlapping trapezia, we're going to get f of 1 here and here. and we're also going to get f of 2 here and here. And also the initial value, f of 0 and f of 3, are going to appear only once. Great. Okay, so that's a nice example there. And maybe if we change the function, we can do one more example and then try and get ourselves towards a nice formula. Okay, let's think of an example. So I'm going to do 5 divided by, and I'm going to do 1 plus x squared. Let's see how that looks. Great. Okay, that's quite good. And I'm going to change my bounds as well. I'm going to do my lower limit is going to be 1, and my upper limit is going to be 5. Okay, so let's approximate the area under there. And I think we're going to maybe stick to our, let's stick to our width of 1. So I'm going to make that have 4 trapezia this time. Good. So we're going to use these 4 this time. Let's write down A, B, C, and D. Label these up. Okay, and let's do these separately. And hopefully our answer is going to be roughly 3.14, which looks surprisingly close to pi, but it's not. Okay, A is a half. F of 1 plus F of 2 times the distance in between, which is again going to be 1, but it's not always, it's going to depend on the question. Okay, let's maybe work this out. So a half, well, I'm actually not going to write this out. I'm just going to type it straight into my calculator. So I'm going to do 5 over 1 plus 1 is 2, plus 5 over 1 plus 4 is 5, divided by 2. Okay, I meant this to be 7/4. It doesn't particularly matter if I get these numbers wrong. The important part is we're looking for the patterns in here. B is a half times f of 2 plus f of 3. Again, times 1 distance in between. Let's type this in. So 5 divided by 1 plus 4 is 5, plus 5 divided by 1 plus 9 is 10. Okay, I meant this to be 3/4. C is going to be a half times f of 3 plus f of 4. And then times 1. So f of 3 I did before. Okay, 5 divided by 10 is a half. 5 divided by 1 plus 16 is 17. Okay, this one I make it to be 27/68. And then finally D, that's a half. And then finally f of 4 plus f of 5. And then again, finally times it by 1. And let's type this in. So 5 divided by 17 plus 5 divided by 26 divided by 2. Okay, 215 over 884. Okay, you can check these for mistakes, but I'm fairly confident with these. Okay, summing these up should make our approximation, which is going to be about 3.14. Let's have a check. Okay, so I'm going to add 27/68. I'm going to add 3/4, add 7/4. Okay, so I get 669 over 221. The decimal for that does match my 3.14027. Great. Okay, so we can do this. If we know what our distance between the strips are, given the number of strips that we've got, I can work out all of these values of y and sub them all into these sums and work out our sums. However, what we can notice is when I'm adding these all together, there's going to be quite a lot of common factors going on. So what we can do is we can generalize this, add it all together and get a nice formula. So I'm now going to draw an arbitrary function and we're going to kind of figure out how we can put this all together. Okay, right, axes I'm going to draw. Okay, and then here's going to be my arbitrary function. And then let's suppose that we want to approximate our area between these values a and b. Okay, so we're going to fill this space up with a bunch of trapezia. I'm going to draw the first few, and then we're going to kind of imagine the ones in the middle. So I've got, try and be accurate here, I've got first trapezia. Maybe make it vertical, that might help. Okay, trapezium number 1. And then next trapezia. And then a few more in the middle. And then the final couple. Great. Okay, let's pretend that these are equally spaced, and then they've got their tops joined with straight lines. So let's do that. Straight line, straight line, straight line, all the way across to the end there. Straight line, straight line. Perfect. Okay, let's think about what these areas are going to be then. So what I'm trying to do is integrate from a to b my function f of x. And the area I get by approximating with trapezia is going to be the first trapezium, which is going to be a half. Now, I need a way of labeling up these x and y values. So what I'm going to do is I'm going to call this first x coordinate x0. I'm going to call this x1, x2, x3, and so on, until I get the final few. So this last one's going to be xn. This one beforehand is going to be xn minus 1. And this one's going to be xn minus 2. Okay, now those are the x values. The heights of these bars are the corresponding y values. So the heights are going to be here y0, y1, y2, y3, all the way up to yn minus 2, yn minus 1, and yn. Okay, so that's what represents these heights. Okay, now I can fill this sum in. So my approximate integral, but this is the exact area, this is my approximate sum, this is a half times y0 plus y1 times the distance in between. Now, I'm going to call the distance in between h, because it's something that we can probably work out. So that's h. Plus, the next trapezium is going to be a half. Then it's going to be y1 plus y2 because of the next strip. Also times by h. And then the third trapezium is going to be a half times y2 plus y3, again times h. And then that's going to carry on all the way up to the end. And then the last trapezium we're going to get is going to be this one, half, and then it'll be yn minus 1 plus yn times h. Okay, that's the sum of all of my trapezia. I'm sorry I labelled it in out of order, but there we go. Okay, so what we can notice now is that there's a lot of common factors here. I can factor out a half from each of these terms and h as well. So let's put all of that at the start. So I've got a half times h. And then after I've factored out those terms, I'm going to get this. I'm going to get y0 plus y1. And then this term is going to give me another y1 and a y2. And then this third one's going to give me a y2 and a y3. And that's going to continue until I finally get yn minus 1 plus yn. Great. Okay, hopefully we can now notice that all of the terms in the middle are duplicates, okay? Which means that we can put them together and take out a factor of 2. So we now got this. We've got half h, and then it's the first y value, and then all of the middle ones are doubled up. So it's 2 times the sum of the middle ones plus yn minus 1, close bracket, and then plus the last one. Okay, that there is the trapezium rule. So what it says is that you figure out the distance in between your strips, that's your h, you put it there. And then inside this big bracket, you've got the first y value and the last y value, and then 2 times the ones in the middle. This is the first y, this is the last y, and then all of these are the middle ones. Okay, and that's exactly how the formula works. So I don't suppose you have to be able to derive this formula, but you do have to be able to use it. It is in the formula book if you want to look it up, but it's worth us having that written down and you know where it comes from. Okay, fantastic. Last thing I want to notice is that we can work out the value of h quite nicely. If we know the number of strips and we know the values of a and b, we can do a calculation to work out h. Then h is, well, it's the difference between a and b, and then dividing that by the number of strips, which is n. Okay, but I think that's something that you'll be able to do intuitively, and the question will make it quite nice. 9 times out of 10, this value of h will be 1 or a half. It doesn't tend to be anything other than that, but we'll see. Right, let's look at some examples, and then I'll leave you to do some in practice. So, questions tend to look like this. Let me move that out of the way. Okay, so this is my function. I don't actually have a picture, but it's we should be able to use the trapezium rule to work out an approximate area. Okay, firstly, we're going to complete the table with the value of y corresponding to x is 1.3, giving your answer to 4 decimal places. Well, here's our table of values. It's just a matter of filling in the relevant ones, and we only need to do this one. Putting x is 1.3 gives us this. Okay, 0.8571. You can verify that with your calculator. Okay, now we're using the trapezium rule with all the values of y in the completed table to get an approximate value for this area here. So we're integrating from 1 to 1.5. That agrees with our table. And our strips look like they're 0.1 in width. So maybe I was wrong there. So 0.1 is our value of h this time. So let's write down our trapezium rule and then plug values in. So we want to do, this is approximately a half h, and then it's y0 plus 2 times. Now there's aren't enough tables in here to need a dot dot dot. I'm going to write them all in. I'm going to have y1 plus y2 plus y3 plus y4, because that's these four in the middle. I've got 0, 1, 2, 3, 4, 5. Here's the last one. It's just a matter of plugging in. H is 0.1. So this is a half of 0.1 times, and then we have to put these numbers in. So it's 0.7071 plus 2 times, and then all the middle ones, 0.7591 plus dot 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 dot, plus the last middle one, which is 0.9037. Close the bracket to stop this 2, and then the last one. Okay, brilliant. I'm going to need to type this into my calculator, and then we can see what we get. So 0.7071, give me a few seconds, I can type this in. Okay, and then divide by 2, and then times 0.1. Okay, I make that out to be 0.41568. To 3 decimal places, that's going to be 0.416. Great. So you need to be showing that you know how to set this sum up, and then you're showing clearly what your value of h is. You don't need to write every single number in your calculation, but you need to make it clear that you've got the first one, the middle ones, perhaps with dot dot dots, the last one of the middle ones, and the very last one as well. That's probably the best way to set this out. Okay, let's maybe see one more example, and then I'll leave you to do some. Okay, right, we've got the trapezium rule written at the top here. We're integrating I, which is sec of x dx, between 0 and pi over 3. Right, the exact value of I then is given by actually integrating this function properly. And thankfully, the antiderivative of sec is given in the book. This is going to be the natural log of the absolute value of sec x plus tan of x. Okay, you can derive this using a U substitution, but it is given in the formula book. We're also going from 0 to pi over 3. Okay, let's just uncover the box so I don't have to waste time. Okay, that ends up being ln of 2 plus root 3, if you type that in. Okay, wonderful. All right, part B. Use the trapezium rule with 2 strips to estimate I. That's only 2 trapezia, but bear in mind that's going to give you 3 values of y. So let's uncover the box. So we're going to use a table of values. The table is going to have x values from 0 to pi over 3, but giving us 2 strips means we need the midpoint as well. So we've got 2 strips either side. So x is 0, y is 1. You plug it into your value of sec x. Pi over 6, you get a value of 1.155, and for pi over 3, you get a value of 2. Again, that's using the fact that my function is sec of x, and that's what I'm plugging it into. Okay, now the trapezium rule says that my integral is roughly a half of my strip size, which is pi over 6 each time, and then it's 1, 2 times the middle one, and the final one, and that gives me 1.39. Okay, 4 strips is going to be pretty much the same, except we are shortening our strip size. So we're going to get a longer table with more values in. We're going to get pi over 12 and also pi over 4 in between these two. Here are the corresponding y values underneath. Again, using the formula, make sure that you're changing your value of h. That's now changing to pi over 12 for our strip size. Again, first value, 2 times the middle ones. The final one is 2, and then that makes 1.34. So as you increase the strip size, these values are going to converge towards our actual answer of ln of 2 plus root 3. I think it might be worth actually working out what that is to see what value we're approaching. So ln of 2 plus root 3 is about 1.3170. Okay, so these values are kind of honing in on that number there. Right, the percentage error in using each estimate, I can give you the sum for that. That's going to be the absolute value, so we don't have to worry about minus signs. That's your estimate minus the real answer as a proportion of the real answer. That gives a decimal, and then you times it by 100 to get a percentage. Okay, so your estimates are these trapezium rules because these are approximations using those trapezia, and then that's the exact final answer. So doing that for both of these gives us these answers: 5.6% and 1.5%. Okay, 1.5% is pretty good. And that's pretty much it. That's mostly what you're asked to do. If you're asked to actually integrate, you're going to need to have some kind of methodology for working out the integration. Otherwise, it's a matter of using this formula properly. Okay, very best of luck then. I'm going to set some questions on trapezium rule, and then we're going to move on, and we're nearly done with integration. Great, thanks year 13. See you soon.